Thank you very much. I'm interested in analysis, but also in a broad range of mathematics. So if it happens that you want to talk about mathematics, it's very likely that I'll be interested. Anyway, today I'm going to talk about the isoperimetric problem in the cube. So what are we talking about? Imagine that you have a room, which is a perfect cube, and you want to split in two regions. One of them of volume 1/3 and the other one 2/3. Imagine that the whole thing has volume 2 as volume 1 using a thin wall. So we're talking about something like this. And this is your wall. And it seems like it splits in two regions and it has a certain area. And the question is, what is the mean area of the wall? If you start thinking about the problem, it's kind of natural to come up with a certain candidate solution, which is just use a flat thin wall as it's used in any apartment in the world. So you just split it in this way. And okay, this achieves area 1, and you might be content or not. There's at least another couple of reasonable candidates that one could think of. Another one, which is pretty natural, maybe you remember the word isoperimetric, often these kind of problems are solved by balls. Maybe it's the case also here. And therefore, you might go for a ball centered around a certain vertex. So you choose a vertex, and you draw the 1/8 of a ball centered there. Well, of course, you have to choose it so that the region is 1/3, which is not the case here. It's a bit less, but okay. And this would be another candidate. One third candidate that in some sense interpolates between the two is this other one. You go for a cylinder around one of the edges. For example, this edge here. This one is also a reasonable candidate. Okay, today I would like to present this conjecture, which is known as the conjecture of the 3D cube, which is one of these three shapes is optimal. Of course, it's not important that the splitting was 1/3, 2/3. You could choose any splitting, and it turns out that the conjecture suggests that one of these three shapes, and of course, given a volume, given a number 1/3, for example, you can tell which one of the three is best. But the conjecture is that this is best in all cases. So, why is it called isoperimetric problem?
Which one is the best for 1/3?
Sorry?
Which one is the best for?
Oh, it's this one. Then you go slightly less, and like 1/π, if I'm not mistaken, and you get this one. And then you get, I don't remember the other threshold, but a bit lower, and you get this one. It's kind of expected that this must happen. Okay, so in general,
is one of the choices like special? Like they have like, they are like critical among like three choices?
This is part of the conjecture. Like you can, of course you can prove, as we will see later, that these are CMC surfaces, so they are critical. Like if you do perturbations that are just local, you are not gonna do anything better. But there could be a very strange, somewhat wide surfaces that does better.
No, I mean, when you change like 1/3 and 2/3.
No, 1/3 and 2/3 is not special at all.
Yeah, I mean, like the probability of like each shape is any of them like measure zero among the choices?
Oh, I'm not sure I understand your question, but once you give me a volume, I can compute which one is the hyperplane splitting 1/3 to 1/3, and I can compute its area, which would be always 1. I can do the same for a ball and the same for a cylinder, and one of them will be winning. But then the question is there another shape that does better? That's the question. I don't know if it answers your question. Anyway, isoperimetric problem in general in a space X. So X, you should think of X as your favorite manifold, for example. If you're not comfortable with manifold, RD is perfectly fine. So, and it's the following simple to state problem. So what is V? V is a volume. And could be infinity. Well, X could be infinity. V cannot be infinity. Is the minimum of the measure of the boundary among all subsets with measure V. Subsets of what? Subsets of your space. Here I am denoting always with absolute value, all the possible measures appearing. Of course, these one are two different measures because this one must have codimension 0 and this one must have codimension 1. For example, in RD, this would be the standard Lebesgue measure, and this would be the n-1 dimensional, the d-1 dimensional Hausdorff measure. Okay, so this is the general setting, and you could see somewhat easily that this one is just a more real-life statement of the isoperimetric problem in the cube. Okay, let's visit some examples that will help us understand a bit better what's happening also in the cube. These examples are very well known, but they are not trivial in any sense. For example, let's start from RD. In RD, you can pose the same question. So among sets with a given volume, which are the one minimizing the boundary, and these are both. This is very well known. The optimal shapes when I say optimal shape, I mean the shape that achieves this infimum, and in particular, you can prove that this infimum is a minimum more or less in all settings. The optimal shapes are both. Then you can ask, I mean, what's the easiest possible manifold you can think of? The d-dimensional sphere. And once again, the optimal shapes are geodesic. Both. Again, on the sphere, does the problem make any sense? Yes, there is a concept of measure and there is a concept of perimeter on any Riemannian manifold. And then there's a third example that maybe it's a bit more convoluted, but it will be important for us, which is the Gaussian space. Here I will not go into details, but there is a certain probability measure that you can put on RD, which is the Gaussian probability measure. This allows you to compute volumes using that measure and perimeters using appropriately that measure. And you can also study the same problem there. And it turns out that the optimal shapes are half spaces. So is this related at all with the original problem, that is understanding the cube? The answer is yes. And this is maybe the only deep thing known about the problem for the cube. This is due to Adwiger, Ross, and probably also someone else. I was unable to find the first one proving this statement. And it's the following thing. In general, the isoperimetric profile of the d-dimensional cube can be bounded by the isoperimetric profile of the Gaussian space. Why do we care? Well, first of all, because, oh, sorry, the other way around. Sorry.
What is isoperimetric profile?
Sorry?
What does isometry?
Right, good point. The isoperimetric profile takes a volume and gives you the minimum perimeter of a set with that volume. Okay, so why do we care? First of all, because this one, we are not able to compute it. This one, we are able to compute it. And it's also pretty explicit. I'm not writing down the formula, but once you know the optimal shapes, it boils down to some computation. And two, this one is unexpectedly much sharper than one would think. For example, as a corollary, you get that when you want to split the cube in exactly two regions with the same volume, which is I'm using the isoperimetric profile to state this result. This is like computing the isoperimetric profile at 1/2, because you want a set with half of the volume, sorry. This one is equal to 1. So this inequality will give you the lower bound. And for the upper bound, to produce upper bound for the isoperimetric profile, you just have to produce an example. And it's pretty easy to produce an example. You just split enough using a flat thing. Okay. And there's another question that one may consider. In the case of the sphere,
Ask the question.
please.
So that you can have a transport map from the Gaussian to the cube, but it's Lipschitz, one Lipschitz, I think.
And I would say that that's really a very good proof of this result.
That will prove this theorem?
Yes.
Okay, so it's nothing more than this. Okay.
No, it's nothing more than this. And still, the first person writing it down, as far as I know, is Ross after 2000. But yes, because I mean, Adviger was proving something weaker than this in 60 something. So I guess he didn't know this one. And it's unclear to me, but Ross doesn't give any reference. But I find the proof incredible, like incredibly interesting and super short, but I couldn't find the reference. Yep, you're right. So, one line proof. That you can have as an exercise. Okay, so for SD, it turns out that up to renormalizing stuff appropriately, you get that this ratio, in fact, goes to a constant as the dimension goes to infinity. You have to renormalize stuff, but I don't want to get into the details. So it seems like the Gaussian space is in some sense the limit of spheres as the dimension goes to infinity. And one may wonder if the same is true also for the cube. And well, this quantity is increasing as the dimension goes to infinity. Well, it's decreasing, sorry. And it's also pretty sharp already in low dimension. So you may believe something like that. And I've shown that, in fact, this is not the case. There is a function g, not 0, so that in general you can have a better bound. And notice that this is not like there must be some work being done, because, for example, g must be 0 at 1/2, because at 1/2 this is an identity, but in general it's not 0 elsewhere. Okay, so this more or less tells you that this inequality is not enough to understand what happens in very high dimension. Maybe we can say something about low dimension, and it turns out that in low dimension we can say a bit more. For example, in dimension 2, this one was folklore and written down by Brézy and Brookstein somewhat recently. In dimension 2, the conjecture holds for the square. So, if you want to start to split a square by using the shortest possible lines, the best thing you can do is to either use a line parallel to an edge or a circumferences around a vertex. So the only two options are this one or this one. Okay, and the other thing, which is also very recent, one is 2024 due to Millman. In dimension 10, the conjecture fails. But this is not unexpected.
Which Millman?
Emmanuel. I don't know what. Yeah. Emmanuel Millman gave a counterexample. The counterexample actually is very easy. Okay, and what about in between? Well, the conjecture is thought to hold in dimension 3. And in my opinion, but this is just my opinion, falls already in dimension 4, because in dimension 3 is already quite sharp. Like, there are almost counterexamples. If I have one more minute, and I do, I just want to mention one thing. How can you go to and try to prove the conjecture in dimension 3? Well, the strategy is kind of the same that you could try in dimension 2, but of course there are many, many more difficulties. What's the idea? And this is something that I mentioned at the very beginning. How do you prove this? Take an optimal shape, E, in the square, then its boundary, which is something that I've never said, but this is very well known to experts and maybe also non-experts, its boundary is constant mean curvature, as constant mean curvature. And this in dimension 2 immediately implies that you are either a circumference or a line. And then using minimality, of E, you control the number of components of the boundary. And this rules out more or less everything but the two options that you know are what you want to prove, like the only optimal shapes, and this gives you a proof in dimension 2. What we are trying to do with a collaborator is to repeat a similar scheme also in dimension 3. Thank you very much for listening.
Questions?
Could you tell what this groove is?
Yes, Gaussian, yes. Go. Not go for that. This is the density.
You surfaces or
Right, good point. So this one gives a density, so it gives you a measure. So when you want to measure, for example, so I move here and I have to explain to you two things. What's the measure of a set and what's the measure of its boundary? For a set, I use gamma of E, which is defined as the integral over E of this density here that I will call rho or phi. Okay. On the boundary, I'm doing exactly the same thing. Notice that here it seems like maybe it's a bit special for the Gaussian, but the same process in some sense works more in general. Like whenever I give you a measure, which is nice enough, you can repeat the same thing. I'm just integrating the same density, but using a boundary measure. This one is this one is a measure that makes sense to integrate over boundaries. What I'm never saying, and in some sense it's 1 century of mathematics, is that you can assume that E is smooth as much as you want, so you don't have troubles with regularity.
Those are questions, though.
What about over finite fields?
What about over finite fields? I guess that there is a certain amount of people interested in proving isoperimetric inequalities in finite fields, and with non-sharp constants. Well, okay, when one moves to the discrete, what I would say is that it's still very clear what's something like this, like what's the volume of something, it's just the number of points in the set. You have to decide what it means to talk about this perimeter. If you are in a finite set where it makes sense to talk about adjacency, then you count the number of pairs that are adjacent, where one is in the set and one is outside. This gives you in general a way to talk about the measure of the perimeter. And as far as I know, there are people thinking about the isoperimetric problem, for example, on grids, for example, on Z2 or on finite things. Like when you say finite field, for example, I would think of as a domain. And it's not important that this is a field, like something like this. And here everything makes sense. And I'm 100% sure that someone proved some non-sharp isoperimetric inequalities. Yes.
One last question.
Oh, maybe this is a bit tangential, but what is known for the ball? If you take a ball.
Right. I think, well, now there's always the issue of giving talks that are recorded, where the chance of saying something false skyrockets. But I think that for the ball, the inequality is known, and it's known to be I would expect them to be geodesic balls. I would be surprised if A, it's not known, and B, they are not geodesic bolts, but if someone in the audience knows that I'm giving the wrong answer to one of the two questions, then please raise your voice.
One last thing.
I'm just curious what you expect the optimal shape to look like when the conjecture fails.
Right. Right. Well, maybe then I can discuss something about the dimension 3. So in dimension 2, as I said, you don't expect, well, already at this level, as soon as you say, the boundary has to be CMC, then you rule out all the non-explicit stuff. But of course, in dimension 3, there is this issue that in dimension 3, there are wide CMC surfaces. And in fact, what we can say, well, we can say something, is that if there is a counterexample in dimension 3, it must be a CMC surface or a minimal one. And we can also say something about its topology. This is at least partially already completely contained in the work of Ross and Rittore.
It will be perpendicular to the boundary.
Yes, yes. This is something I should have said maybe here, but by minimality, you not only know that it's CMC, but it's free boundary, which means that it touches, in the picture it's true, but I forgot to say it. It touches the boundary orthogonally. And you can tell what the topology of an optimal shape should look like, and it should look like something like this. Maybe it's absolutely not clear, but there are 3 branches and then it's connected. The topology is non-trivial, but also not too complicated. And we know that this kind of stuff exists. Like there are, for example, both minimal surfaces and CMC stuff with this topology. And we also know that they go very close to the optimal. Like Ross mentions this in a paper. Something reaches something, like there is a certain splitting where you would expect this to be the winner. You have a certain splitting using this kind of surfaces, which is completely different, but achieves area 1002. It is almost false. That's why I think that in dimension 4 is, yeah.
Okay, so now we'll thank the session.